Hello, my name is Alexei. I'm a PhD student at University of Toronto, and today I will introduce you to our project titled Optimizing JIT Service in the Cloud with Code Caching and Speculative Compilation. This work is a collaboration between University of Toronto and IBM. Managed language runtimes, such as the Java Virtual Machine, use just-in-time compilation to achieve optimal performance. During application startup, the JVM slowly interprets the bytecodes and collects profiling information. Frequently executed or hot methods are then compiled into optimized native code in the background. While JIT compilation improves performance, it comes with a significant overhead. The JVM may need to use up to hundreds of megabytes of extra memory, and the CPU overhead can reach dozens of % of overall CPU usage. The additional memory footprint leads to lower application density in the cloud because execution environments such as containers need to be provisioned with more memory. The CPU overhead becomes large for short-running workloads such as function as a service. The JIT server technology implemented in the OpenJ9 JVM aims to solve these issues by decoupling the JIT compiler from the rest of the JVM and moving it to a remote process. This disaggregation allows the client JVMs to run without the additional footprint, improves cold start performance in resource-constrained environments, and enables us to provision and scale the resources used for JIT compilation independently from the resources used for running application code. However, this design has important drawbacks. If we consider both the client JVM and the JIT server, the overall CPU usage is always higher compared to local JIT because of remote compilation overhead. JIT server also suffers from network latency. A large number of messages are exchanged between the client and the server during compilation, and high network latency slows down this process. We address these issues in our work with two complementary approaches. First, we cache compiled code at the JIT server to reuse it for multiple JVMs running the same or similar applications. This reduces overall resource usage, since the cost of JIT compilation is now amortized over many clients. Remote compilation latency goes down because cache hits only need a single network round trip. Second, we predict what application methods become hot and compile them speculatively at the JIT server before the client would normally request them, effectively hiding compilation latency. Caching compiled native code at the server is not a trivial task. Compiled code is specific to a JVM instance and cannot be reused as is in a different JVM. OpenJ9 supports dynamic AUT compilation, where it generates relocatable code that can be reused in other JVMs running on the same machine. We extend dynamic AUT to support correctly reusing compiled code in any JVM running on any host connected to the JIT server. The implementation of this approach is complete and is currently being contributed to OpenJ9. We show that caching compiled code at the server significantly improves performance. We use the amount of useful work done, for example, number of requests served by an application, per second of total CPU time used, including the JIT server, as the measure of CPU utilization. Caching improves this metric by up to 2 to 3 times and reduces start time by as much as 50% compared to JIT server without caching. In our second approach, we use machine learning to predict what application methods will become hot in the near future, so that JIT server can compile them earlier. The machine learning model is trained on the history of compilation requests in previous runs of the application and exploits similarities in the request sequences from run to run. This work is still in the early stages. To summarize, JIT compilation overhead and managed runtimes leads to lower application density in the cloud. JIT server uses remote JIT to address this problem, but its design results in higher overall CPU usage and suffers from network latency. We solve these issues with two approaches: caching compiled code at the server and predicting hot methods to compile them at the server earlier. Caching achieves up to 2 to 3 times better utilization of CPU resources and speeds up cold start by up to 2 times. That's it. Thanks for watching.